Good morning, everybody. This is Javier from the Department of Construction and Building Technology of the Higher Polytechnic School of Madrid. In the next few minutes, I'm going to show you the work entitled Analysis of a SLAM-based laser scanner for the 3D digitalization of underground heritage structures. A case of study in the wineries of Baltanas, Palencia, Spain. This work has been developed within the framework of the Cost Action Underground for Valley. This presentation will be structured as follows. First of all, we're going to make a short introduction about the complexity of the study case, as well as the remote sensing strategies that we have nowadays to digitalize this type of heritage. Then we will go to the materials and methods section, on which we will describe the sensors used as well as the methods suggested for comparing both sensors. Then we will go to the experimental results section, on which we're gonna evaluate these results through a discussion of them. Finally, we will close this work with a set of short conclusions. The study case used for this work is the underground wineries of Baltanas. Baltanas is a small village located at the north of Spain, more specifically in Palencia, Castile and Leon. This underground complex is the largest one here in Spain, and is made up by a total of 374 wineries, distributed in a total of 6 different levels, as you can see in the right image of the slide. In contrast with this, relevance that seems to have this complex, its location in a small village and inside the ground, demands its proper digitalization, in order to generate a virtual platform that allows us to promote this wonderful piece of architecture. From the previous slide, we can extract the following conclusions about the general characteristic of this underground heritage. No light conditions, narrow and irregular spaces, and no GPS or positional data. These properties make really difficult the use of common remote sensing strategies, such as the photogrammetry, since we don't have light condition and we have also narrow spaces, as well as the terrestrial laser scanner, since we have narrow spaces. Being the unique feasible solution, the use of the novel mobile mapping systems. These systems, the MMS, are remote sensing methodologies that are able to digitalize an environment in a dynamic way without requiring the use of any positional system. This system could be classified in different typologies, such as vehicle-based, trolley-based, or the wearable mobile mapping system. The last one, the wearable mobile mapping system, it's a type of mobile mapping system that allows us to digitalize an environment with just only walking through them and handle the laser head by a unique operator. As you can imagine, this solution is really flexible and productive. This type of sensor, the wearable mobile mapping system, are based on the well-known simultaneous location and mapping algorithm, which allow us to generate a 3D point cloud by registering in an incremental and iterative way different set of bidimensional point clouds, as the user can observe in the image placed at the right. However, this type of sensor shows a highly dependence with respect to the data acquisition protocol, as well as many variables to be taken into account during the processing stage. Both questions modify the final accuracy of the product and need to be taken into account in a proper way. In the image placed at the right, you can see the different variables that are taken into account during the processing stage. Global convergence, window size, voxel density, rigidity, and prioritization to planar surfaces. The meaning of these variables are explained in more detail in the proceeding. So, the main focus of this paper is the evaluation of the wearable mobile mapping system during the data acquisition and processing with the aim of obtaining the best ratio accuracy processing time. In other words, we are going to develop a optimal methodology for the digitalization of the wineries of Baltanas. In order to make it possible, it was chosen as a study case the largest winery of this complex. These results will be extrapolated to the rest of the wineries in order to obtain a world 3D model. In order to carry out this method, we use the wearable mobile mapping solution CEP-RIVO from the GeoSLAM company, as well as the terrestrial laser scanner Faro Focus 120. The last one will be used as ground truth to compare the discrepancies of the SLAM solution with respect to the truth. The first one is able to capture near 4,000 points per second with a nominal accuracy that varies from 1 to 3 centimeters. Meanwhile, the second is able to capture near 1 million points per second with a nominal accuracy of about 2 millimeters. The weights of both sensors are similar, around 4 kilograms. As we exposed previously, we will use the terrestrial laser scanner as the ground truth. According to this, we carry out a total of 22 scanning stations in order to digitalize the whole winery. Then the data capture was aligned in a unique reference system by using the iterative close point algorithm. Result of this, we obtain the whole 3D point cloud of the winery, as the user can see in the right part of the slide. After this, we carry out the digitalization of this winery by using the wearable mobile mapping solution. In this case, we follow a set of good practices that includes the use of closed loop paths, in other words, that the start and the finishing point are the same, as well as a constant walking speed. A total of 2 protocols were tested during this phase. The first one is the standard protocol, and the second one is a proposed protocol, which is the cross protocol. Regarding the first one, the data acquisition was carried out by pointing out the laser head in front of the direction of movement. This protocol is the common use with this type of sensor, but generates, in this case, there and back paths that could reduce the accuracy of the product. On the other hand, the non-standard protocol, the proposed one, that we called the cross protocol, in this protocol, the laser head is crossed with respect to the walking direction, as the user can see in the lower part of the left image. This protocol minimizes the there and back areas, expecting higher accuracy than the standard one protocol. During the processing stage, we solve several times the SLAM problem, one time per different values of processing variables we have. If we remember, these variables are convergence threshold, rigidity, window size, voxel density, and prioritization of planar surfaces. A total of 30 and 80 SLAM solutions were solved, half from for the standard protocol and the other for the proposed one. Each one of the solutions were registered with respect to the ground truth, which is the terrestrial laser scanner point cloud, by using the iterative close point algorithm. Then the discrepancies between each solution and the reference one was performed by using the well-known algorithm M3C2. This algorithm is a highly robust discrepancy evaluator of point clouds and is implemented in the open source software Cloud Compare. In the images of the slide, you can see the discrepancies of the SLAM point clouds with default parameters. As you can observe, the upper one, which is the results of the standard protocol, shows higher discrepancies than the lower one, which is the proposed one, especially in the entrance of the winery. As we said previously, we are going to evaluate the point clouds in terms of processing time and accuracy. This graph shows the different time consumptions for solving the SLAM problem when we change one variable per time. The meaning of each symbol could be consulted in the proceeding. Overall, the data acquisition protocol does not have influence in the processing time. Apart of this, we need to highlight that if we increment the local convergence variable, the time consumption increments in a strong way in comparison with the rest of the variables. This increment could be observed in the left part of the graph. In this slide, you can see the results of the statistical analysis carried out on each SLAM solution. During this stage, we perform a normal test, in this case, the QQ plot, in order to see if the discrepancies follows a Gaussian distribution or not. In all the cases, the discrepancies does not follow a Gaussian distribution. According to this, we use non-parametric indicators such as the median, the MMAT, and the square of BWMV. All of them give us an idea of the accuracy of each SLAM solutions, since lower values, especially in the median and the MMAT, indicates lower bias and dispersion of the discrepancies. In all the cases, the cross protocol, which is the proposed one, outperforms the standard protocol. Apart of this, we carry out an interpercentile range evaluation in order to see the expected results in terms of confidence intervals. As it is logical, the proposed protocol has lower values in comparison with the standard one. Then, a discussion of the results was carried out with the aim of understanding the source of discrepancies of each case. In general terms, the bias and the dispersion of the results are lower in the cross protocol, and the time consumption is similar. With respect to the variables of the SLAM problem, the convergence threshold increase the quality of the final point cloud, but is the most critical in terms of processing time. On the other hand, the window size and the rigidity also increase the quality with lower impacts in terms of time, but need to be taken into consideration the use of extreme values that could lead in non-proper solution of the SLAM problem. The voxel density also has a similar effect, but with lower increase of quality. As we expect, the prioritization of planar surfaces does not have any impact due to the irregularity of the static cases. This parameter could be neglected in future processing stages. The results obtained during the previous section move us to the following conclusions. The terrestrial laser scanner obtained a high accuracy 3D point cloud, but with a density of about 5,000 points per meter square, but requires 5.5 hours. In contrast to this, the wearable mobile mapping system shows lower accuracy, about 1 to 3 centimeters, and a lower density, but requires just only the 8% of the time to create the 3D point cloud. The cross protocol outperforms the standard one. So we can conclude that the wearable mobile mapping system is a feasible solution for digitalize the wineries, or in general terms, underground heritage, but requires the use of cross protocol, which is not the standard one, in order to increment the accuracy of the final point cloud. This work is enclosed within the framework of ELISA and the cross-action underground for value. The first one is a European education initiative devoted to develop the new European engineer. More specifically, this work is enclosed within the sustainable BCC community, devoted to teach European engineers in the field of sustainability. Many thanks for your attention. If you have any question or suggestion, please contact with us through the mail provided in the lower part of the slide.